and gentlemen, John Belkowitz here, Director of R&D Intelligent Concrete. We are going to talk about how do you make concrete that bends. When I was a younger man, full head of hair, working at Lafarge, somebody presented me with an article from a university, and it showed a thin concrete beam that was like bent in like almost like a U shape, and it blew my flippin' mind. And if you don't know, concrete is very much like a ceramic material. It doesn't like bending. It doesn't like atomic dislocations or having an elastic region. It has more of a plastic fast fracture region. I mean, it still does have an elastic region, but it's a very small region, and the strain upon failure is very, very small. It doesn't like tensile stresses, and it doesn't like coming back to its original shape. So when you see a concrete beam that can bend in a U shape and then come back to its original form, just absolutely amazing. So somebody posed the question, John, how do I make a concrete that can do that? We're talking about concrete. We're not talking about grout. We're talking about rock and sand here with a binding matrix, great concrete coming down the chute. So how do we make concrete that bends? So we're starting with the mix design, and that's really everything that it comes down to. It's not the way that we're going to apply the forces, although that will have a certain impact, but we're just saying a concrete that can bend and return back to its original shape, and that has to deal with the composite structure. So the first is the balance behind the binding matrix and the granular skeleton. Now, the binding matrix is the piece of the puzzle, or the composite, that is of the ceramic nature, that does not like, changing its shape and then going back to the original shape, that volume change. So that's what we really have to give the ability to dislocate on a very atomic level, almost like a plastic or a rubber-like material. The aggregate, as long as it's part of that binder matrix and within, it's not going to have a major impact. It's really more to take up room, be the less expensive alternative to take up volume, and then not take away strength or those fresh properties. The thing about the granular skeleton, though, is that we can actually use tougher materials, rubber or fibers, to create a ductile tearing or blunting of the localized stress that would cause those catastrophic forces to cause cracking and even contribute to that atomic dislocation that we see with bending. So, I mean, that plays on the second thing of the mix design, fibers. And there's so many different directions that we can go with fibers. If we're going to go the ASTM route, there's a certain size of fiber, so we're talking about macro fibers and, steel or macro synthetic. In this case, I would say more like your macro synthetic fibers that have more of a plastic or an e-glass material concept to them, or material design, I meant to say. And it's not just the plastic fibers that we're looking to have in that resiliency. The steel will, but it will take a lot more force, and unless you're going for higher loads than we're talking about, and there might be a certain residual stress that the steel imparts onto the concrete as it goes through those more extreme bending angles. So there's that part to consider, but there's also the gradation of our fibers, where if we took too much of one size of fiber, we might get some nastier fresh properties. So when I say gradation, I mean just like we would a granular skeleton, a gradation envelope, or different sizes of that one fiber, and or using a microfiber, whether it's a mined material, synthetic material, that will have an impact on a mechanical scale, as well as a molecular interlocking scale, and then finally carbon nanotubes, or even smaller than that, your nanoparticles, which again will have more of an impact on the chemical and molecular side to absorb those catastrophic forces, as well as contribute with those atomic dislocations. The next piece of it, and it's the second to last one, is the different liquids that we can put into our concrete mixes. And when it comes to creating a hydrated cement matrix that is tougher and less brittle, there is some research that shows that you want to reduce your calcium silica ratio. And if you think about it, we're talking about the sheets of our calcium silicate hydrate, and that's the brittle material. I mean, the unfortunate reality is that making those calcium silicate hydrates, they are a ceramic-like material. So by incorporating more or higher ordered silicone into that, or silica into that gelled hydrated cement matrix, we can effectively make that matrix less brittle and more tough by putting more calcium in there. Let's say if we loaded the system up with calcium chloride, you would be effectively increasing strength, but also reducing the strain at which that hydrated cement matrix is going to fail, and in essence making it something that would not be able to absorb those catastrophic forces and be more of a brittle-like material. The last piece that I wanted to discuss when making a concrete that bends, and more than likely we're going to do a concrete mix design and put it in samples and go through some bending and see how it works out and show it to y'all. So we'll do a formula or a concrete mix design portion of this, but the last piece of it is the sacrifice. And this is something that I often talk about when it comes to road patches or quick patches, where, I mean, the sacrifice in fresh properties is more accepted. But when it comes to concrete, like we did a video on self-healing concrete, or concrete that can bend, you're creating a very high performance concrete. I would almost say ultra high performance concrete. And maybe not in the strength state, but in the performance features and benefits, especially when you're creating a concrete that can bend or self-heal. So it should be expected that there is going to be a sacrifice in something else. You can't always have your cake and eat it too, or get the best of every single world, especially with how technology still needs to go through its adolescence or its infancy, adolescence, and then more maturing. With self-healing, we might have been using it, or I'm sorry, with bending concrete, we might have been using it for years, but we're still waiting for those major advances in concrete to get past the unfortunate reality that not only might you see sacrifices in your fresh and hardened properties, but if we're talking about concrete, a Portland cement-based composite, the backbone of it is still a ceramic-like material. And it might be able to bend and go back to shape for a few cycles, but the unfortunate reality is eventually through fatigue, that system will fail if the fatigue cycles are strong enough, or they happen over a long enough period of time. But at a certain point, that hydrated cement matrix is going to go through some type of failure mechanism, and there's nothing wrong with that. Creating a concrete that can go through a bending process is a pretty awesome flipping thing. So I hope you enjoyed today's video. I had a great time talking about it, and I know the team is going to have a great time talking about it later in the team talk. If you have any questions, any comments, throw them below. Don't forget, like and subscribe, and check out the Concrete Note, great podcast where we go over some of our new technologies. Go concrete, beat asphalt. Thanks a bunch.